Now we start for mapping, multiphysics, and acoustics. An important part of solving an aeroacoustic problem is to correctly map the CFD solution onto the acoustic domain. This is done using the built-in background fluid flow coupling, the BFFC multiphysics feature, and the dedicated mapping study. Okay, so first we go to physics and add physics. From add physics, we choose acoustics, aeroacoustics, and then we choose a linearized and Navier-Stokes equation frequency domain. Go to the interface and clear here the CFD study. We will not solve that for CFD. We just solve it for acoustic. Add to component 1. Okay, so we have linearized and Navier-Stokes equation now. We have multiphysics between the turbulent flow and linearized and Navier-Stokes equation. Okay, which is the BFFC, background fluid flow coupling. So we select background fluid flow coupling, and settings, select domain selection. From the selection list, choose all domain and locate the variable to map here. What we want to connect between the turbulent flow and linearized Navier-Stokes equation. We connect the pressure, the velocity. Also, sometimes we connect density if it is compressible flow, and turbulent viscosity. Okay, and then we create the acoustic mesh that the CFD solution is mapped onto. The mesh can be relatively coarse. Note that the finer the mesh, the less damping is introduced by the stabilization. That is present to stabilize a sub-mesh physical phenomena like velocity wave. At the wall, we don't resolve the acoustic boundary layer since slip and adiabatic condition are used here. 1 or 2 boundaries layer mesh element is enough to resolve the background flow profile near the wall. In the component toolbar, add mesh. In the label, we will call it mesh / acoustics. As we say, the mesh will be much coarse. In the mesh toolbar, we click free tetrahedral. In the tetrahedral, we go to size. In the setting for size, locate the element size. In the custom size, locate the maximum element size, and then type d main over 8 for the maximum element size, and for the minimum element size, we will put d main over 15. For the free-fed tetrahedral, in the setting window, locate the domain selection. For the geometric entry label list, choose domain. In the domain, select 2 and 5, 2 up to 5 and 7 and 8, 2. We will not select 1, 2, 3, 5, 4, nope, 6 not, 7 and 8. We will leave 1 and 9. We will add size feature to the tetrahedral. In the setting window for size, locate the geometric entity selection. Okay. In the geometric entity selection, from the geometric entry label list, choose boundary. We're gonna increase the mesh here. From the geometry entry level list, choose boundary. We can select 26 only. So we'll come here, Control A, and then remove all that only leave 26. We choose this area here. Locate the element size section and choose custom. In the custom, locate the element size parameter section and choose maximum size parameter, checkbox, and we put here the main over 50. So we're gonna increase number of elements here. Return back to mesh, choose sweep, and just sweep, choose distribution. In the distribution, locate the distribution selection, and for number of elements, type 16. And then we have the boundary layer. In the boundary layer settings, click to expand the transition. In the transition section, clear the smooth transition to interior transition. Boundary layer properties. In the boundary layer properties, locate the geometric entity selection. That's it. And then, from selection list, choose wall. Locate the layer section in the number of layer text field, type 2. From the thickness specification list, we go to thickness of first layer. Choose manual. For the thickness, we're gonna put the main over 40. This is the thickness of the layer. And then we push Alt O. We can see here for the free tetrahedral, he made all that as a free tetrahedral with this size, okay? But he increased the size here in this region smoothly, okay? In 1 and 6, we choose sweep and we make a distribution number. So this distribution, there are 16 layers, 16 number of element, and then the boundary condition, the boundary layer. Okay, here we have the acoustic mesh. We continue to add a study of mapping. So we go to study and then add a study. In the add a study section, we have mapping here. We gonna solve checkbox of turbulent flow and checkbox of linearized universal equation. It's only for background flow coupling. And then we say add a study. So we have study 2 here. Change the name of the study. Study 2 mapping. Go to study, solution to map. From the study list, we choose study CFD stationary. We map CFD stationary. From the solution list, choose solution 1, what we just solved it. From the parameters, value, we choose all. So we can solve for all Mach numbers. So now compute. You will do mapping for all values of Mach number. for demonstrating the values coming from mapping study, we're going to compare the Z velocity from the CFD study and the Z velocity coming from mapping study. And we also will compare the turbulent viscosity coming from CFD study and the turbulent viscosity coming from mapping study. So first here we choose 1D plot group. From 1D plot group we choose line graph for Z velocity coming from CFD. In the 1D group we type mapping comparison Z velocity. CFD study. Okay, here we're gonna select edge number 12. The expression Z velocity will be W. We can see its velocity field Z component with meter per second. In the X component, we will have an expression. The expression will be X. So he will plot the Z velocity in the direction of X with every point of X. And then we go to the ligand, show ligands, we turn it to manual, and then in the manual we write Mach number equal and Mach number equal, and then we show ligand here. So we have the first is Mach number with 0.1, and there this is a Mach number with 0.05 coming from CFD study. Okay, here we have a line graph too for Z velocity coming from mapping study. Also, we gotta choose 12 here. And then the Y expression will be coming from insert expression here. First, we should select the study, like we have study 2, solution 3. And then from insert expression, we go in component, we can find background flow fluid coupling. And then from that, we choose the velocity, the mapped turbulent viscosity, the mapped pressure, the mapped density. We have the mapped velocity. In X direction, Y direction, Z direction, we have the velocity in Z direction. Okay, the units will be meter per second. And then the expression, it's X expression as before. We go to the color and style. We try to make dashed so we can differentiate between that and that. And then to the ligand, from automatic to manual, show ligand. I'm gonna say here Mach number equal, and then Mach number equal. So we have here, you can see how is the mapped velocity the same as the CFD velocity, except in some small region lead the walls because of the slip boundaries, and as we say, the adiabatic boundary. So we're gonna go to turbulent viscosity. We choose 1D plot group. Okay, here we will write mapping comparison turbulent viscosity. From here we choose line graph for turbulent viscosity. From safety study we go here, choose the same place, which is 12 here, and then from the expression we're going to see the expression. We should first choose the case to safety study, solution 1. Choose from turbulent, so turbulence variables we have turbulent dissipation, turbulent dynamic viscosity, which we want dynamic viscosity, Pascal second, and x we choose expression to be x as we did before. Then solid, show from automatic to manual, can choose here Mach number equal 0.05 and Mach number equal 0.001. We have the two things here. Second line graph. This is the line graph with turbulent viscosity from mapped study. We have the same place here, and the expression we should choose study, and then the expression to be here from mapped turbulent viscosity is be from mapped turbulent viscosity velocity magnitude here, mapped turbulent viscosity with Pascal second. Then we choose, we will change to be dashed. It's with expression x. Show ligand, manual, Mach equal 0.05 and Mach equal to 1, and then we choose plot. We can see as we see they are the same, almost the same. The difference is just only near the walls. So we were sure that the two things that we wanna, that the velocities and the turbulent viscosity, they are the same. We can do that for temperature, for density, as we wanna, for sure that the mapping is doing a good job.